All right, welcome everybody. Today we're going to talk about Calc Lesson number 76. This is still section 7.1, area of a region between two curves, but please note that this is day 2. So we're going to start with a reminder of what we did yesterday, and then we're going to see an alternate technique. So here for number 1, notice it starts by saying in terms of x. That's all you've learned to do so far. You're going to find the area bounded by those curves there. Notice I have a little reminder for you there highlighted in blue. Those are some integration formulas for how you would integrate with the natural log. So we're going to need that. When you see in terms of x, please make sure you know that in terms of x is always meaning top minus bottom, which again is all we've learned so far, but we're going to change that in a couple of minutes. But for now, in terms of x always means top minus bottom. So if you take a look over here at the curve that I've graphed for you, notice first that y equals 10 over x. That's a rational function. A rational function has 2 branches. It has horizontal asymptotes. It has vertical asymptotes. That is the graph that is in blue. Notice there are 2 pieces. There's the piece in the first quadrant, and then there's also a piece in the third quadrant. Turns out the piece in the third quadrant isn't really relevant to this problem since it has to intersect x equals 0, y equals 2, and y equals 10. So we're really focusing on the first quadrant. When you're doing top minus bottom, the majority of the problems that you've seen and done so far have only had one top and one bottom. But as I mentioned yesterday, the top and the bottom can switch at some point in the interval, and that's exactly what happens here, leading to more work. So as you start doing top minus bottom, notice that between x equals 0 and x equals 1, your top is the dotted line and your bottom is the black line. Once you get to 1, however, though, your top is actually 10 over x, where your bottom is y equals 2. So I'm going to go ahead and highlight this area, but again, I'm going to use 2 different colors to highlight the 2 different regions, meaning that there's a different top and bottom for the different colors. So again, here is my first unit. Then I have a second shaded region that is here. And again, we did see some like this yesterday, so it's not that it's brand new, but the thing is, whenever you have to split the interval, it winds up being more work, which is why today is going to show you a shortcut of sorts, as long as it's applicable. So let's take a look here. We have the yellow and we have the orange. Hopefully you remember from yesterday that if you're trying to find the area, you're going to set it up as an integration. And in this case, we're going to have to set it up as 2 different parts. So the first integration for the yellow, we're going to set it up from an x to an x. So that means from 0 to 1. If you do the top minus the bottom for that specific interval, the top curve is y equals 10. The bottom curve is y equals 2. So top minus bottom is just 10 minus 2. And then that's going to need a dx. And again, a little bit of color coding. This is the yellow region. Then you're going to add it to the orange region. So the orange region exists from 1 to 5. The top curve in that case would be 10 over x. The bottom curve would be y equals 2. And that's going to need a dx as well. And again, a little bit of color coding, just showing you that this is the orange piece. So not that it's terribly difficult, but again, hopefully you can agree certainly that it is more work than if you were just able to do a single top minus a single bottom. So from here, let's go ahead and integrate and evaluate each piece. So starting with the first part, 10 minus 2, that turns out to be the integration. We're not actually going to solve yet. We're going to still keep my integration. So 10 minus 2, that just turns out to be 8 dx. And again, that's still from 0 to 1. Then I'm going to separate this second part here as the integration of 1 to 5. Of 10 over x dx minus the integration from 1 to 5 of 2 dx. So all I did was separated it into 3 different portions, which is just going to make it a little bit easier to integrate one at a time. So from here, if I'm going to actually go ahead and integrate now, if you integrate 8 in terms of x, that's going to be 8x, and you're going to evaluate that from 0 to 1. Plus, if you're trying to integrate 10 over x, you're going to need this reminder here. The way that you would integrate 1 over x, you would integrate it the same way, except you would need a 10. So this would be 10 times the ln of x, which you would then evaluate from 1 to 5. Minus, if you integrate just a 2 in terms of x, you're going to get 2x, and that's going to be from 1 to 5. So again, those are my integrations. I'm going to need a little bit more room, so I'm just going to scroll on over there to the right. But again, just to kind of reiterate what I've done so far. So the graph was given to you. As you try to find that bounded region, you notice that the top and the bottom change throughout the interval. So you have to write one integration there in yellow, then a second integration there in orange. And then I decided to break up the orange integration as well, because I knew that I was going to integrate the 10 over x slightly differently than I integrated the 2. So now I'm going to have to go ahead and calculate that, which I'm going to do here over on the right. So let me just copy that again. This is 8x, and I'm evaluating that from 0 to 1. Then I have to evaluate 10 times the ln of x from 1 to 5 minus 2x from 1 to 5. So I'm going to go ahead and evaluate each piece. So starting with the 8x, if I go ahead and evaluate that, I'm going to plug in the 1, which is going to give me 8 minus 0. Plus, for the middle, I'm going to get 10 ln of 5 minus 10 ln of 1. And again, just as a reminder, it's always a subtraction in between. Remember, that's the fundamental theorem of calculus. Minus, if I plug a 5 in for the 2x, I get 10 minus 2. So now as I go to simplify here, 8 minus 0, that just becomes an 8. You may or may not remember, it's an extra variable there. So 10 times the ln of 1. The ln of 1 is always 0. So that means that this is just going to turn out to be 0. So plus 10 ln of 5 minus 8. Turns out that the 8s are going to cancel out, which means my final answer to this problem is 10 times the ln of 5. You are more than welcome to leave that as your final answer. You could find the decimal equivalent if you wanted to, but no need to. So 10 ln of 5 turns out to be the final area of that region. So again, let me just kind of bring it on back here just so we can see the entire thing. Remember, you're doing top minus bottom whenever you're doing it in terms of x. You're going to integrate each part separately. You're going to evaluate it using the fundamental theorem of calculus. And your final answer, you're going to get a fair amount of ln's anytime there's a rational function involved, which is perfectly acceptable. So how is it going to change for today? Well, notice that here in number 2, you have the exact same problem. You have the exact same equations, but notice here that they're asking you to do it in terms of y. So if they're asking you to do it in terms of y, you have to look at it in a different way, which means instead of doing top minus bottom, you're now going to think of it as right minus left. And again, we're going to summarize that as a formula on the next page, but you're now going to do it as right minus left. So if you think of it as being right minus left, and you're thinking about the same region here, the right curve is always going to be the same, and the left curve is always going to be the same. So the way that you had to split up the first version, you don't have to do here, because again, the right curve stays the right curve the whole time, and the left curve stays the left curve the whole time. Now, there is one slightly different thing that has to happen here. If you're doing it in terms of y, your equation has to be x equals instead of y equals. So in most of the problems going forward, that will already be done for you. But in this case here, we have to do it for ourselves. So you're going to take this equation, y equals 10 over x, and you're going to rewrite it as an x equals. So how do you do that? Well, you first cross multiply. So xy would equal 10. Then solve it for x equals, so x equals 10 over y. So if we're doing this problem in terms of y, that is the iteration of the formula that I'm going to need. And then it turns out when it comes to everything else, the x equals and the y equals, those are good to go because those are just vertical lines and horizontal lines. So again, we're now going to do this same problem, and we should get the same answer or an equivalent answer as number 1, but now we're going to do it in terms of y's, which means we're going to do right minus left. So as I go to set up this area, this is going to be the integration, not from the x bound to the x bound, but from the y bound to the y bound. So if you take a look at this problem, the y bounds are 2 to 10. So that's the first thing you have to be really careful of whenever you're doing it in terms of y. You have to do it from the appropriate y to the appropriate y. The right curve is the rational function, which we've resolved it for here. So you're going to do 10 over y. That's the right curve. Minus the left curve is the y-axis, which is just x equals 0. So 10 over y minus 0. When you're doing this in terms of y's, you're going to use a dy, not a dx. Might not even need this step, but it's still going to be an integration. And of course, anything minus 0 just stays the same. Even though you're doing this in terms of y, you're still going to use those ln formulas that are highlighted in blue above. So the way you would integrate 10 over y would be 10 times the ln of y. And again, it really should be the absolute value, I guess, in the previous one as well. Sorry about that. So then you're going to go ahead now and evaluate that from 2 to 10. So if you evaluate that from 2 to 10, you are going to get 10 times the ln of the absolute value of 10 minus 10 times ln of the absolute value of 2. Notice that you can, of course, factor out a 10. So that would be the ln of 10 minus the ln of 2. Hopefully it hasn't been so long. If you look there, remember, if you have logs of the same base, you're allowed to go ahead and turn that subtraction into a division. So this is going to be 10 times the ln of 10 over 2, which, would you look at that, simplifies to be 10 times the ln of 5, which is, of course, the same exact answer that you got to the problem above, and that always should be the case. Whether you do it in terms of x or in terms of y, you should get the same answer or an equivalent answer. If it doesn't look exactly the same, it usually just means you have to use a little bit of log properties to get them to be exactly the same. All right, so we just saw the same problem done two ways, one in terms of x and one in terms of y. And so now we have a slightly new formula. If you're trying to find the area between two curves and you're doing it in terms of y, notice that instead of f of x, it's f of y. Instead of g of x, it's g of y, and you have to make sure you do dy. Notice that instead of a to b, it's c to d, where those are the y bounds. You're always going to assume that f of y is the right curve and g of y is the left curve. So instead of top minus bottom, you're always going to do right minus left. And notice that just like before, the right and the left curve can switch throughout the interval. So let's take a look at a few more of these. Here in number 3, notice that the problems are already x equals for you. So sometimes you're going to have to solve yourself, and sometimes it will be given to you. So notice that in this case, x equals y plus 1, that is still just a line. Where x equals 3 minus y squared, that's a quadratic. Notice that it faces to the right because a positive y squared would face to the right, a negative y squared would face to the left, just like a positive x squared faces up, where a negative 1 faces down. If you were trying to find the area of the region bounded by those two curves, looks like you're going to be highlighting this region in here. And again, you should be highlighting on your notes as well. This is an easy version of the problem because, again, everywhere in the interval, the right curve is going to be the dotted line, where the left curve is going to be the solid line. So it's not always that it's going to be the case that there's no switching, but you certainly want to be on the lookout for ones that are. So as you go to set up your integration, so the area is equal to the integration. Again, the number one thing you have to watch out for here is you have to make sure that you're doing it from the y value to the y value. That's probably the number one mistake that we see. So negative 2 to 1. You're going to do the right curve. So the right curve is 3 minus y squared minus the left curve, which is y plus 1. And again, that whole thing should be dy. Still the integration from negative 2 to 1. You're going to go ahead and distribute and simplify. And then I'm going to just rewrite it. So negative y squared will go first. Negative y. You're going to get a 3 minus 1, which turns out to be a positive 2 dy. You're now going to go ahead and integrate each of those values one at a time. So negative y squared becomes negative y cubed over 3 minus y squared over 2 plus 2y. You're going to go ahead and evaluate that from negative 2 to 1. Remember your fundamental theorem of calculus. You're going to start by plugging the 1 into each of those values. So if I plug a 1 in, I'm going to get negative 1/3 minus a half plus 2. Remember, fundamental theorem of calculus is always a subtraction. So now I'm going to plug this negative 2 in, and you just want to be extra careful. So when you cube a negative 2, you're going to get a negative 8, which if you then make it negative becomes positive 8/3. If you square a negative 2, you're going to get a positive 4. So that becomes minus 4 over 2, which becomes minus 2. And then minus 4. Again, from this point, you could either find common denominators or you can use the calculator. Either way, you're going to wind up with an answer of 9 over 2, or perfectly fine to find the decimal equivalent of 4.5. So this is going to be my answer here to this problem. And again, this is just reiterating the idea of right minus left. And again, making sure you're doing it from Y to Y, which again is probably the most common mistake. So try not to make it. All right, and for our final problem here, it says find the area bounded by the given curves, and notice it says you're going to set it up but not solve. The setup is really the most important part. Notice that even though it doesn't differentiate specifically whether you're doing it in terms of X or Y, if you have X equals, that's the clue to you that you're going to be doing right minus left, dy, as opposed to the other. And again, sometimes it will say which way to do it in terms of X or in terms of Y. Something pretty interesting is happening here in that you are going to have to be splitting this interval. So again, notice you are looking for the region bounded by the positive quadratic to the right. Again, a positive y squared will face to the right. The vertical line x equals 5, y equals 3, and y equals negative 3. So there's not just one bounded region, but there are actually 3 of them. And so you're going to have a different right minus left for each of them. So notice that that is the first region up top there. Notice that the second region is here between the curve and between x equals 5. So again, hopefully it stands to reason there's a different right minus left there than there was in the yellow. And then you actually have a third little region here where it goes back to the original. So again, I would highlight them each. I like to use different colors. You can certainly do what works for you. And again, you want to pay attention to these y values to make sure that you are integrating in the right locations. And again, think about how much harder and more time consuming this would be if you were asked to graph it and find those points of intersections on your own. But again, our gift to you is we're going to be telling you what they are. So that'll save you a lot of different time here. So you're going to go ahead and find the area, and hopefully it makes sense that there's going to be 3 integrations. So you're going to go ahead and start, and I'm going to work from the bottom to the top. So I'm going to start with the orange. So if I'm integrating the orange, I am going from y equals negative 3 to y equals negative 2. If I'm doing the right curve minus the left curve, the right curve is the quadratic, which would be y squared plus 1. Minus the left curve would be 5, and that whole thing would be dy. And again, a little bit of color coding. I'm just working from the bottom piece to the top piece, and it actually doesn't matter which order you put them in. So then I'm now going to have to add this to the blue part. So the blue part goes from negative 2 to positive 2. If you're doing the right curve, that's going to be 5. If you do the left curve, that's going to be the quadratic, y squared plus 1. And again, this piece would have to be dy as well. And I'll just go ahead and color code that for you. Then finally, you're going to have to add the third slice, which is the yellow slice, which goes from 2 to 3. And again, if you're doing the right minus the left, you're again starting at the quadratic, which would be y squared plus 1 minus 5. And that whole thing would be dy as well. And again, just a little color coding to make sure that you understand. So for you to actually do those subtractions, integrate and plug the numbers in, I'm reasonably confident that you would be able to do that. But the truth is being able to understand the setup, the right minus left, the correct variable, and the correct integration bounds, that really is the most important part. If you find yourself in a situation where you'd like to go back and actually do it to practice the algebra, make sure you know the final answer should be 46/3. Otherwise, the setup will be sufficient, and it's possible that for future homeworks or problems, you'll be asked to just set up as opposed to solve, just to make things a little bit easier. So on the homework tonight, there's 4 problems. The first 2, you're going to do it right minus left, and then on the back, you're going to do one of them in terms of x and one of them in terms of y. Should be pretty straightforward if you just read carefully. The truth is, this is my final video of the year for you guys. So for the final time this year, thanks very much for tuning in. Unfortunately, I won't catch you next time, but thanks.